Direct, inverse, and joint variation. These are special types of relationships variables can have with each other. The first one, a direct type of relationship, we can say that y varies directly as x if y is equal to k times x. K is some constant that we're multiplying by x to get y. And that constant remains the same in this particular relationship. So k is not equal to 0, and k is a constant like a 5 or a 1/2 or even a 0.35. This type of relationship is also known as a proportional relationship. We're multiplying x by a k to get y. So let's look at some examples of direct variation. So if we have y equals 5x, that 5 is my constant in this case. I'm always multiplying x by 5 in order to get y. So k is 5 in this case. Looking down here, we would say d varies directly as t. So notice we don't have to use y and x. We can use other variables, but we have to be explicit about what's varying to what. So we have d varying directly as t. So here I have 3.5 times t. Whatever my t values are, I'm going to multiply them by 3.5 every time. And that's all I'm going to do. So my k is 3.5. That's my constant. In this case, my constant is a fraction. Y equals 2/3 x. Y is equal to 2/3 times whatever x is. My constant is 2/3. Here, if it's written differently, you can rewrite it to see if it can fit this form. In this case, I can multiply both sides by x, and I have y is equal to 5/3 x. 5/3 then is my constant. Y equals 5/3 x. My k is 5/3. Now, if I have something like this extra additional 1, I'm not always multiplying x by something in order to get y. I'm also adding 1. So this is not an example of direct variation. It has to just be multiplied by that constant with no additional addition. So let's look at an example of what we can do with this information. If y varies directly as x, and y equals 9 when x is equal to -15, find y when x is 21. So we have a lot of information in there. The first piece of information is we know y is varying directly as x. So y times some constant, y equals some constant times x. So y equals kx. Now, if we knew what this k was, we could find everything, right? Because we know we multiply whatever x is by k to get y. So we're going to multiply that 21 by k, but we don't know what k is. Well, luckily, this relationship works for everything. And so we can use what we know up here. We have a value that we know is true. When y is equal to 9, x is equal to -15. So I can substitute those values, 9 in for y, -15 in for x. So I have k times -15. Now I can solve for what k is. I'm just going to divide both sides by -15. And when I do that, I have k is equal to -9/15, or 9 over -15. Now simplifying that, I have k is equal to -3/5. Now I know my k. I know this relationship now is always based around multiplying by -3/5. So I can take the k in my direct variation right here, my equation, and I can substitute in the -3/5 for my k. Now I can multiply my x, or 3/5 times my x value, which is 21, and I can get what y is equal. So -3/5 times 21 is going to give me -63/5. So y is equal to -63/5 when my x is 21 in this particular proportional relationship. So let's take a look at the next type of relationship. That's inverse variation. Now, inverse variation, because we're talking about a multiplicative sort of relationship, inverse would be the multiplicative inverse. And so instead of having x in the numerator, I have k over x. Y is varying inversely with x. K is not equal to 0 and x is not equal to 0. So y varies inversely as x. So here I have y is equal to 5 over x, and if I were to look for the constant, I just look for that constant over the x, and that's a 5, so k is equal to 5 there. In this case, my constant is 2/3 with my x in the denominator. Here, it's not solved for y, so it's a little bit difficult to see. If I divide both sides by 3x, this side by 3x and this side by 3x, I get y equals 1 over 3x. And now I can see my constant is 1/3, so k is equal to 1/3. This equation is not an example of inverse variation. I have a fraction right here, but my x is in the numerator, so this is actually direct variation. It's not inverse variation. And this, again, as well, I can't add those additional numbers on there. It has to be a variable or a constant over that variable with no extra addition or subtraction. So let's look at an example of how to use this. Y varies inversely as x, and y equals 4 when x equals 12. Find y when x equals 5. So we would like an equation that would work for all of these relationships. We have one particular instance when we know it's going to work, but we would like an equation that always will tell us what y is when we know what x is. And so because it's inversely, I know right away to write it as y equals k over x. Now if I can solve for that k, I'm all set, because then I can find out what y is when x is equal to 5. So first let's solve for k using what we know. Our known values have to make this true. So we're going to substitute a 4 in for y and a 12 in for x. Now we're going to solve for k, because if we can get k, we can find any values using that relationship. Multiply both sides by 12, and I have 48 equals k. I'm going to go back to my inverse relationship right here. I'm going to substitute 48 in for k, and now I can use this to find y when x equals 5. I'm just going to substitute a 5 in for x, and I'm not even going to simplify that fraction. I'm just going to leave it as an improper fraction. Y is equal to 48 over 5. And I could simplify it depending on the circumstance and what is needed. The last relationship actually relates 3 different variables. It's called joint variation, similar to direct variation. Y varies jointly as x and z if y is equal to some constant times x times z, where k is not equal to 0. So some examples of this. We have y equals 5xz, so my constant there, my k, is 5. And here, we need to solve for our y to see if it can fit this form. So multiply both sides by xz, and I have y equals 3xz. My k is 3. Over here, similarly, we're going to solve for y to see if we can get it into this form to see if it's a joint variation. Multiply both sides by 2, and I have y equals 2xz. Y equals 2, that's my constant, xz. And additionally, if I added things to the end of this, that would not be joint variation. It has to just be that multiplication relationship. So let's look at an example, and it's probably the most complicated example, but if you remember what joint variation is, you'll be able to take it step by step and do this type of problem. The area of a trapezoid varies jointly. So right away, you know you're going to have some variable equal to a constant times 2 other variables as the height and the sum of the bases. So we don't have x's and y's and z's in this case. We have the area varying jointly. So the area varies jointly, I know there's going to be a constant k, as the height h, and as the sum of the bases. So when we add base 1 and base 2 together. So my area equals kh times the sum of the bases, b1 plus b2. So the question asks us to find the equation of joint variation if the area is equal to 48 inches squared, when h equals 8 inches, my height, and my base 1 is 5 inches, my base 2 is 7 inches. So using this information, I should be able to come up with an equation. Now the only thing I'm really missing in this equation is this constant. This constant's going to make this work every time. So given a height and 2 different bases, I can always find the area. Conversely, if I know the area and I know the sum of the bases, I can find the height as long as I know k. So that's my job, my goal. For my equation, I need to find k. Now I know this is true for a particular case. I can use that case and the knowledge that it varies jointly in order to solve this. So I'm going to substitute the values I know in. I know the area. My area is 48 inches squared equals K times the height, which is 8 inches, times the sum of the bases, 5 inches plus 7 inches. Now I can go ahead and add those together to get 12 inches, times 8 inches, times K equals 48 inches squared. When I multiply these inches, I get an inches squared here, and an inches squared is still here. And I have K times 96 inches squared is equal to 48 inches squared. Now I can just divide both sides by that 96 inches squared. 96 inches squared. And divide this by 96 inches squared. And that's going to give me, 48 is actually, if I double it, I get 96. This is going to reduce to 1/2, and my inches squared cancel each other. So my K is equal to 1/2. Now I'm going to take that back in because I want to find the equation of joint variation. That's this right here. I'm going to take this K equals 1/2, and I'm going to substitute it up here. Now given a height and the sum of two bases, 1/2, the height and the sum of two bases, I can find the area. Or if I'm given the area and the sum of two bases, I could then solve for the height. So this is the general equation for the area of a trapezoid. And I know that because it both varies jointly and I was given this specific case.